Welcome to the reading group. This week, Hong is going to be presenting the AIE Flow. Take it away.
Yeah, sure. So hello everyone. Today's topic is about the AIE floor, which is, uh, you know, yeah, it's the floor, uh, beneath what, James has already discussed, in the last, reading group session. So basically for the MLIR AIE floor, as we can see, the input for this flow is basically the uh two part. Yeah, it's like the C++ kernel, and the other one is the data flow graph, which describe how those kernel uh interact with each other. And the output for this flow is the host control program, like running in the CPU side, and also the AIE engine binary, uh, which is basically the XL bin and or the configuration static configuration files for the AI engine or NPU side. And inside this flow, it can also be divided into two main stage. So, yeah, from the left side, it's what we call the FIFO level logic mapping. So, yeah, as we can see, the blue arrows describe the communication or connections between different types. Uh, yeah, and at a yeah, and with the MLIR AIE compiler, uh, yeah, this logical mapping can be further lowered to like some physical mappings, which basically did the routing like uh, to decide which switch box or which channel we should use to realize those logic pivot or logic connections. So this is just an overview for the MLIR AIE flow, and we will dive into the details in the following slides. So yeah, here are some like basic introduction to the AI engine tile components with the representation of AIE dialects. So as we can see, uh, the AI engine tiles. Can you see my pointers like in the sharing screen or?
I cannot see your pointer in the sharing screen. Oh, it kind of blinks. Now I can.
So yeah, probably need to turn to see extra point. So yeah, as we can see, the AI engine tiles are the basic building blocks for the of the AI engine design, and it is declared as AIE.tile and with the coordinates inside of the parentheses. And the two major components of AI engine tiles are, the VLIW processors highlighted in the green box, and uh, it can be declared as the AIE.core and with the tile name given by the entire declaration. And the other major component is the local memory buffer. It's highlighted in blue, and it can be declared as AIE.buffer, and with the data type it stores in the memory modules. And there is a third key component which is not shown in the uh, in the in the in the code example here is called the lock, which is also a crucial component for synchronizing data between different tiles and also between tiles and the host controller. Yeah, I mean this might not be a very big physical. Yeah, I mean this might not be very large physically, but it's very important to facilitate efficient and correct the data communications. So yeah, that's oops. Yeah, that is basically the uh wait. Yeah, that is basically the AI engine tile components represented by the AI engine dialects. And so yeah, I will. Yeah, and after the overview of these tile components, we now move on to one of the uh, major components of AI engine system design is called the communications. So in AI engine architecture, the communication file, the local memory for those adjacent tiles is one of the most efficient way to share data, and this can be done like among four, yeah, I mean among up to four tiles adjacent to like a local memory. And in the diagram here, we can see that the local memory for the tile uh, 2, 4, which is on the row 2 and column 4, is basically adjacent to the core in the tile 1, 2. And if we expand the diagram further, we can see that the tile 2, 3 and the tile 2, 5 uh, can also access that buffers inside the tile 2, 4. So in general, each processor can access a memory in its own tile and also the memory of the tile to the north side and south side, and the memory like either to the east side or the west side, depending on which row this tile is located at. So yeah, and also the code examples here shows shows you know, a tile communications, a local memory tile communications using the log dialect explicitly. Like, yeah, so you can see here, it acquired the logs, uh, inside the tile 2.4, and yeah, which basically transfer the ownership of these buffers to like uh the other tile, and then it's write do the like read write operations. So yeah, I mean using the log dialect uh to build the yeah, I mean to achieve the communication is straightforward. But for some other scenarios, maybe a higher level abstractions for communications might make it much easier to reason about and to develop some organization strategies. So yeah, the object FIFO is the higher level abstractions, which is used to establish the communication across the AI engine array without uh, without explicit configurations of those AI engine type components such as the logs, switch box, or whatever. So yeah, this object FIFO here, basically declare like the producer tiles and the consumer tiles, and the size of, the size of the data it wanted to transfer, also the data type of the data it is transferring. So yeah, and this object FIFO is then like lowered to onto the physical MLIR-AIE components uh using the like the compiler conversion path. So yeah. And so far we have discussed like how communication works between adjacent tiles through like sharing local memory, right? So for non-adjacent tiles or tiles that are far away from each other, the communication is instead done through the tile DMA and also the switch network. So in the diagram here, uh, Yeah. In the diagram here with the object FIFO we introduced in the previous slides, we can see that there's no visible or huge difference uh, between like object FIFO declarations. Uh, yeah, I mean with adjacent tiles and the one with non-adjacent tiles. What we need to put here is just a producer tile and the yeah, uh and the consumer tiles. So we don't care whether they are adjacent or not.
What's the one mean? Is that the lock that's used or something else?
Here the
Yeah.
one means the size or the depth of the data. Uh, yeah, yeah, the size of the FIFO. So
Like the depth.
yeah,
It's a one word FIFO. Is
yeah,
that what that means?
yeah,
Okay.
yeah, and uh, yeah. I mean under the hood. The lowering of this object FIFO will instantiate the tile DMA like of this tile memory module, and as well as the stream switch network like belongs to these tiles for communications between non-adjacent tiles.
Let me ask
Yeah.
another question. And if I'm asking questions that everybody else knows, just tell me, stop asking so many questions. Okay, so that's FIFO with one word. That's what the one means. Is that right?
Yeah.
And then but then it's got like a property on it of like a type of AIE object FIFO, which is 256 words by 32 bits wide.
Mhm.
What does that mean? I mean, it's a memory buffer, but is it saying like that's what's connected on the other side? Like, how do I interpret that?
I think
Or is what it's
yeah,
going into?
the memory type, the memory wrap, like this one is just the type, the logical data type. This object FIFOs, yeah, is about to transfer. So
Okay.
yeah, like yeah, it's like what kind of data it stores in the FIFOs for the communications. So,
Okay.
So
Hong, quick
sorry.
question about the previous slide. Oh, Andrew, do you have questions?
the previous one or this one? Oh, sorry.
Uh, sorry, the slide prior to this, the lower level language with the lock.
I don't know if you have your monitor maxed out. If you could, is that the max volume on your laptop?
Me? Oh,
Yeah, I think it's the maximum
Okay.
value.
I can talk
Just
louder.
speak loudly, Alex.
Sounds great. I'm wondering, I can see that there's an acquire of a lock, but I don't
Mhm.
see a release. Is this just omitted due to just not enough space, or does their locking because I saw that there was a release in their higher level language with the FIFOs.
Yeah, actually for these examples, yeah, it's just for
I
demonstrations.
see.
Yeah, and also it is worth mentioning that, yeah, as we can see, the use log and it specified the acquire operations, but there's also like one here, which is
Oh,
used to distinguish the read access or write access. So yeah, if it's only for read access, yeah, I guess it can be like yeah, it's like some read write log. So it can be more efficient, like just obtain that log.
I
Yeah,
see.
it's only for read purpose. So
Thank you.
yeah. And yeah, I guess like normally we would put like the acquire and the release like to uh yeah for the like the critical sections inside of the yeah code instructions, but this is just for demonstration. Yeah. And sorry, Andrew, what is your question? Yeah.
Yeah, so I had a question about this. So no, go to the next one. I think it's related to the FIFO question that Colin
Mhm.
asked. So I guess what you mean here is that this one word deep, each word is of the type 256 by I32, right?
Oh, yeah.
Is
So
that,
this is
okay, so I say take the product of those things. So that's what you're saying. So it's one word, but a word is huge.
Yeah.
Because that memref You're not sending a pointer to that, like you are
Mm.
actually sending like, you can send entire 256 words that are each 32 deep
Mm.
or 32 wide. Is that right? Okay.
Yeah, it's only the logical representations, and yeah, I guess at this level it has nothing to do with the like the physical, for example, the channel ads or that sort of thing. So yeah, it's
I
only
see.
the logical representations for the
Okay, so
like
one word, but the word can be huge. Like
yeah,
here, the word means 256 by 32.
yeah.
Okay. Mhm.
But I guess this kind of like leads to my next question is like, what is the significance of this number? Like if I take this one and change it to 2 or 4 or 8, right? How does that make a difference to the mapping to the hardware?
I think it might has to do with like how large the buffer you need to allocate like for the the DMA modules or the intermediate tiles in the path of that fiber. So
I see.
yeah,
So it's just for memory allocation. So you can think of
yeah,
it as like the size of the memory that you're
yeah, yeah,
allocating.
yeah.
And it's basically one multiplied by the size of the type, which in this case is 256 by 32 bits.
Yeah.
I
Yeah,
see.
and I guess uh another like advantage of these object FIFOs AMD guys mentioned in the I mean in their slides is that this object FIFO interface like kind of combine the data allocations and the data movement inside one statement. So
Yeah, because that
yeah,
size is presumably just at the two endpoints.
yeah,
It'll allocate
mm,
probably that whole buffer on each side. Or maybe it's a bit more clever and allocates a little
mm,
more than half on each side or something, right?
mm,
But in between, it's all just the hardware, so there's very limited buffering, I think.
mm.
Okay, I think I understand it.
And then like my last question is like, is there a way for the programmer to say something about the criticality of this communication channel? So something like, oh, I want to prioritize this for latency, for example.
Um, yeah, I mean, as far as I know, there might be, uh, yeah, I guess there's no such like configurations or like interface to specify that, criticality.
I
But
see. So you're
I
basically specifying channels and then you're at the mercy of the basically routing optimization
yeah,
routine.
yeah,
Also, their dominant, I mean, the hardware can do packet routing, but their dominant use of it, I think, right now is that they statically configure the switches, right?
yeah, like the circuit switching mode.
Yeah,
Oh, I
circuit
see.
switch, but I think it's also like circuit switch without, I think they can reconfigure it, but I don't think they do reconfigure it right now. Or at
Yeah,
least it's not
yeah,
exposed very well in the programming model, at least.
mm,
So that would also mean, yeah, you kind of either get it or you don't. Does
yeah,
that make it?
I
So
see.
criticality would probably only affect do you get a direct route or not.
Yeah,
And
I was thinking more in packet
so,
switch.
yeah, well, they can do packet switch. So this is where you get into like their hardware can do more than their programming model exposes very well.
mm,
So
I see. And the reason why tile 20, like tile 24 is between braces is that you can do like multiple destinations. So you're kind of like broadcasting a
yeah,
specific object
yeah.
FIFO.
Yeah, exactly.
yeah,
Yeah, I guess this broadcasting, yes, on the like the for future slides, like
okay.
I
yeah.
see. Okay. Okay.
So
I'm glad you asked that. I was wondering why it was. I thought it was just like that was just that's the way you felt like writing it. So yeah.
Makes sense. Thanks, Hon.
uh yeah, and I guess we um, oops. Okay, so yeah, I guess we have already discussed this, right? So yeah, it's like for the non-adjacent tiles, we yeah, we still stick with these like object FIFO representations, and there's no difference between like non-adjacent and adjacent, like using only this interface. And there will be like some uh lowering like lowering paths for the basically do the routings to lower these object FIFOs to DMA, which locates at this like memory module, and also allocate the switch network along the paths it find. So yeah, I guess one interesting thing about this lowering is that, yeah, let's say for this object FIFOs, it needs at least 3 switch box along the path, right? So yeah, so for the middle one, like the routing process still need to, uh set some informations for these intermediate tiles, yeah, just to access or allocate the switch box belongs to these tiles. So yeah. So yeah, I guess in that case, the placement and the route might be much more complicated because yeah, we have also need to deal with all the intermediate tiles during the placement or during the routing process. So yeah. And so yeah, now that we have seen the how point-to-point communication is handled, right? And here we introduce the one-to-many broadcast, and this is necessary like if we have data, for example, sent from the external memory, and we need to broadcast it to like multiple destinations. And yeah, and this is also important because we have a very fixed set of the routing resource, and we need to be very efficient, like to move data to avoid any congestions. And here, yeah, we put like multiple like consumer tiles inside the breast here, and yeah, I guess the rest of them are just yeah, pretty similar to the previous example. And yeah, that's all. Yeah, and that's all because of these abstractions of the object FIFO. So yeah, Alex, go ahead.
Yeah, so I had a quick question. So when I think of a broadcast, let's say the
Mm-hmm.
message is the letter A, all
Mm-hmm.
the consumers would receive the same letter. They all get A. But when we're talking about FIFOs, I think of it like a bin where the producer will fill the bin with the letter A, and the consumer is the first one to reach into the bin and grab the letter A will get it.
Mm-hmm.
So if I'm the producer, I put A, B, and C into the bin. That will get distributed A, B, and C to multiple people. So which is it? Is this a do when I put some when the producer tile 14 puts something into the FIFO, does tile 34 and tile 35 both receive the same packet?
Uh, yeah, I think for the broadcasting, uh, there will be like some duplication logic when they're into the like the some physical AIE components, right? There might be some duplications when uh yeah, when for example the Taiwan send a packet to like multiple destinations, the Taiwan might do the duplications and put each packet into different FIFOs. So
So is
yeah.
the packet duplicated? In like, for example, in this example, will tile 34 and 35 receive 14?
Receive 14?
Yeah,
Restore
Oh,
because
data.
you're storing it.
okay. Yeah, you mean this
Will
one,
they
right?
both see 14? I know it's always going to be 14. Let's say the first time that tile 14 produces something.
Yeah, the first tile, like the Taiwan 4, right? They
Yep.
produce some values and
I guess it produces an input,
yeah.
and then you basically, an input buffer, like this example is just randomly choosing entry 14 in that data transfer.
Hmm.
I think that's what, val input, well, I guess it's choosing what's at 3.
Yeah.
at index 3, and it's storing that 14 at that point, right?
Mhm.
Mhm.
Uh, let's see. I don't know if I can I can understand that much.
I guess I'm just confused by whether this is a broadcast or if this is a FIFO.
It is a broadcast. I
Mhm.
mean, it will go to both for sure.
Mhm.
The same will go to both. Okay, cool.
The same data words will go to both. Like that switch that has two arrows going into it is going to be I forget exactly how they do it. Maybe Andrew remembers. They configure it to basically have two paths go across there.
Hmm. I see.
And I can't remember, they had some complicated way, maybe you remember, Hong, like they had some complicated way of doing this. Like they think they kind of stacked packet headers. They got stripped off.
Yeah.
It's kind of a bizarre
Mm.
way to do it. Maybe that was actually how they traversed the various routers as they went through.
Mm.
But it would take 99% sure it follows like kind of both those paths. That's how they do the broadcast. So
Hmm.
I think you're asking, is it considered received when one thing gets it or when both get it? It would be like both.
I
Mm.
see. Thank you.
Yeah, and yeah, I guess the like there will be like some future topics here. So yeah, I guess the first one would be like the cascade streaming, which is another like specialized data transfer strategy between, horizontally adjacent tiles. And uh yeah, I mean currently there are some features like for supporting this cascade streaming, but not fully worked in the uh yeah, MLIR-AIE ecosystems. So yeah, to do that, we need to rely on some external compiled kernel functions, which is basically the production flow, like using the Fides to do that. And also for the packet switch mode, uh, yeah, yeah, I guess what you mentioned, like the package header, that kind of thing.
Yeah.
Yeah. Uh, so in the packet switch mode, we use some like pre-appended packet headers, uh, to to send a package from the switch box to the switch box. And I guess in that case it works like similar to the circuit switch mode, but just with some additional headers and also the signals for that. But yeah, I guess I can prepare more like for this part. Yeah, maybe in the future reading group.
Is that exposed in the MLIR AIE?
Yeah, it is
It
exposed.
is exposed,
Yeah,
so you can use either circuit switched or the packet switch mode.
yeah.
Okay, that's interesting.
And yeah, and also I guess like switching between these two modes is not that hard from the dialects perspective. It's just a change like a few interface. And uh so yeah, that's what I learned from their like example and tutorial. And also for like L3 external memory, uh I guess today we only discuss like the communications inside the air engine array. So to transfer data from the L3 DDR external memory to the local memory or the L2 memory tiles, it need to deal with the like this shim DMA, which requires more like you know yeah, more components uh that need to be written in the AI dialects. So yeah.
Okay.
Yeah, I guess that's it for today. Any questions for
Yeah, I have a question.
Mhm.
What was the benefit of going into the MLIR dialects instead of writing this either just directly writing into some assembly language or using LOVM or something like that? Is there a reason like do you find any optimizations in MLIR they're doing or anything that's like MLIR specific?
Yeah, I think this can goes to yeah, I guess using MIR yeah, MLIR is basically uh yeah, as we can see for this AIE.core, there is a lot of like instructions running inside the per core processor, right? So with the MLIR support, yeah, we can combine, some other dialects in the, some other dialects which supported by the MLIR compiler into this flow. So
Mm,
we can, for example, we can use arrays or memory ref to uh yeah to write or to transform or yeah, I mean to get the uh per core instructions. So
mm,
yeah, I guess that's one of the benefits of using MLIR so that we can port like different type of dialects uh, into this flow as long as it is supported by the MLIR compiler. So
mm,
yeah, and it's also worth mentioning that the MLIR-AIE also support like linking with externally compiled kernel functions
mm,
and put it into this core AE.core bodies. So yeah, we can utilize some highly optimized uh like the per core code uh yeah for the AI engine design. So yeah.
mm. Thank you.
Yeah, any
Any,
other questions?
mm. I guess I can ask another question. I'm a little lost in like trying to visualize what would be like an application that would run on this, that with all these producers and consumers and smaller cores. So, for example, let's say I was doing something simple like a matrix multiply, which James was talking about last week.
Hmm.
What would each core be doing, and what would the data transfers look like, just at a high level? I'm just curious.
Uh, I think if we take like what James discussed in the last sessions, for example, the AIR flow, right?
Hmm.
So let's say a matrix modifications, uh, it yeah, if we put it in through the AIR floor, we can get the partitions. Uh, like for example, each tiles compute like part of the small matrix modifications, right? We can get that partitions uh for each engine tile, and uh yeah, there will also be like some data sharing, which requires the you know yeah, which requires, some communication patterns like this, right? Or even broadcast to send the factors uh yeah into multiple engine tiles. So yeah, I guess in that case, each tiles would run like a small partitions of the small matrix modifications, and there will be like some data sharing between different tiles, or a tile need to grab some data from some uh external memory or L2 memory. So yeah.
Oh, I see. So it would be like some of these tiles will be like, we'll have FIFOs that bring in, let's say, an A and a B. It produces a it does the matrix multiply and writes it onto a FIFO for the result. And there are some tiles that do, like, let's say, a reduction, which will add all that information together. And the
Mhm.
final result will show up on, let's say, the L3, for example.
Yeah.
Gotcha. That's really
I
interesting.
guess the way I think of it is you'd probably tile it
Mm.
as you were saying, Hong. So you'd be doing multiply and accumulate and reduction inside an AIE on two tiles, like an A tile and a B tile, and producing a partial sum for a C tile.
Mhm.
You could pass that partial sum of the C tile to another AIE that has produced another partial sum for the overlapping C tile, like the same C tile, and as it goes through and you do that final spatial reduction, you would now have a complete C tile.
Mhm.
And um, and then you can have other things working in completely different C tiles that don't overlap.
Mhm.
And then every once in a while, you need to broadcast move your B array around.
Yeah,
Like
yeah.
take this tile needs to go to some other people to start computing the next piece of C and so on.
Mm.
So there's a lot of different ways you can actually, surprising number of ways you can actually split up matrix multiply.
Mm.
So I guess where like Charm and Max Eva come in, where they basically tried to work out efficient ways to do matrix multiply on the AIE array.
Mm.
Um,
Mhm.
do you agree with what I just said, or would you
Yeah,
say
yeah.
no,
Yeah,
that's not
exactly.
right?
Yeah.
I don't know if that's helpful, Alex. I think that for a matrix multiply, I think their dominant flow would be like tiling and then you get a lot of options, but like a
Mm.
common one would be like produce sub pieces of the C subtiles or C tiles that have to be kind of reduced to get the
Mhm.
full output of this piece of C.
Mm.
Yeah, that makes sense. I was just curious, like, what would it look like? Because it looks like the grid of tiles has the opportunity to have a lot of spatial parallelism and also to do like almost like compute in memory because you have these little pockets of memory that can like bring the data along with it. So I'm just very curious how they do this, and that is really cool.